to the Engineering Center for this evening's lecture. And I will start off by saying a word of prayer. Shall we pray? Father, I want to thank you so much for this evening, the wonderful opportunity to come into your presence and into this important lecture. I want to thank you for the life of our speaker and her family and for all those who are joining us. We pray that this evening will be a fruitful, enriching time, that we will all be blessed and enriched in our knowledge of the subject. In the name of Jesus we pray. Amen. Amen. All right. Thank you very much for the opportunity and for being with us this evening. First of all, I want to introduce myself. My name is Engineer Asare-Yeboah. I'm the chair of the electrical division of the institution. And our speaker for this evening is Engineer Dr. Kyeiwaa Asare-Yeboah, who I would describe as a daughter of the house. As a daughter of the house, she's the daughter of our past president, Engineer Asare-Yeboah, and also a member of our institution, because a few years ago, I had the opportunity of joining a panel that interviewed her to become a member. So she's a bona fide member of the house. And ever since, I think that first interview session, I always was telling her that she would have to give us an opportunity to tell us about the work that she's doing, because it was through her that I heard of organic electronics for the first time. And even though I've been in practice for more than 20 years, I hadn't heard that that was a new evolving area of our practice. So I immediately told her that we would have to have an opportunity where she would come to speak to us and tell us about the subject that she's been working on. So the discussions have been going on for a while, and so when she mentioned that she was going to be in Ghana, we went further with the discussions, and then decided that while she's on her holiday, we would probably find some part of the holiday to do this lecture. We juggled it a bit, and finally we landed today, and that's why we are here. And we're hoping that we'll have more people, and maybe I apologize for not having a lot of people in person. Our people have gotten used to doing online ever since COVID, and we are struggling to bring them back, but hopefully we would have ways to bring them back so that we can have more in person. But online, I believe we have more than 30, 50 people now online who are, so as I said, they've gotten too much used to being online. So, but I believe the subject is very important. So without much further ado, I would want to hand over to our lecturer for this evening, Engineer Dr. Kyeiwaa Asare-Yeboah from the Penn State University, Behrend. And she's going to talk to us on organic electronics, materials, processing, and applications. Thank you very much.
All right, thank you for that fine introduction, Engineer Asare-Yeboah. Thank you all also for coming to listen to my lecture, and for those online too, thank you also for being here. All right, so I'll just kind of dive right in and go through what I'll be talking about today. Right. So I'll first introduce what inorganic electronics are, because they are what we are actually using. And if you don't know it, when I introduce it, you know exactly what I'm talking about. Then I'll go into organic electronics itself, which is my field or my area. I will then go through some fabrication methods. I'll focus on a specific organic electronic material and look at different methods that I use to fabricate it. And then go into a specific fabrication method that I developed called the temperature gradient technique. And I'll also talk about why it works for depositing these materials, and then conclude from there. Now, I'm an electrical engineer, but as I go through the lecture, you realize that there'll be a bit of chemistry involved, there'll be a little bit of physics involved. This area actually encompasses an area called material science. So there are lots of different engineering groups and also people in physics that actually study material science, right? So before I kind of go into what the inorganic electronics are, I want you to appreciate the size or the scale of materials that we actually deal with. All right. So starting with just making relationships between measurements and then materials that we actually know. So human hair, the size of the human hair is between 50 and 180 micrometers. All right, so if you just take one strand of human hair, that is the size that we have. Now, the electronics that we deal with are much, much smaller than that. All right. Then let's just talk about the fine beach sand. Fine beach sand is about 90 micrometers. I won't go through all of them. I'll skip to the dust particles. So dust particles that we see typically are less than 10 micrometers. Then the respiratory droplets. So what we actually don't even see, usually you have that around 5 micrometers. So between 5 micrometers and 10 micrometers will be what our respiratory droplets are. Then we all are familiar with this, unfortunately. Coronavirus, the virus itself is about 0.1 to 0.5 micrometers. Now, obviously, we can't see the virus with our naked eye, right? And the electronics that we deal with can go even smaller than that, all right? So with that being said, there are different types of ways that these electronics can be made or fabricated. Typical conventional manufacturing, if you think about just maybe like a general motor that is manufactured, or maybe let's take an example like a gear, right? If a gear is about 4 inches in diameter, you'd have a typical manufacturing process that we use. It can be made through casting, forging, or machining to actually get the gear structure, right? Usually, we would have that in a size that is greater than millimeters, right? Then we have micro manufacturing. Micro manufacturing usually would have other methods. One is called lithography. Lithography is really using light and lenses to transfer pattern onto a small substrate or a body, essentially. Right. Etching is just taking away materials. Coating is adding materials. So micro manufacturing falls within this. And for micro manufacturing, usually you are looking at less than the millimeter scale. And micro manufacturing was actually developed because of processes, essentially the semiconductor devices that we use. Okay. Then you have one that kind of falls in between the macro and micro manufacturing, which is known as the meso manufacturing. Right? And those would be small motors, small devices like your sense, hearing aids, or electronic toys. Again, tiny devices there. Then we come all the way down to nano manufacturing. And for nano manufacturing, again, that is the scale that most of the devices that we work with when we talk about our cell phones here. The electronics that are within the cell phones are typically made in the nanometer scale. All right, so for the inorganic electronics, they are based on a material called silicon, mostly. Silicon is an inorganic material. is actually gotten from sand. And typically what happens in silicon is made into what the image that you see on the left here is known as an ingot, which is just a really pure silicon material that is formed into a crystal. The electronics are made pretty much from this silicon material. This ingot is cut into something called wafers or substrates, which you see on the right-hand side, right? So the devices that we have, or for the inorganic materials, they are created on these wafers, right? The wafers, typically, the diameter ranges, they have different ranges, but the typical one would be around 300, about 300 millimeters. Typically, I deal with it in inches, so 4-inch, 6-inch, 12-inch wafers. Right? And the image that we see on the left side here is one that actually has devices made on it, right? And we go through different processes, steps. Lithography, like I mentioned before, is one of the processes that's used to create the patterns for the devices. It goes through etching, it goes through thin film deposition. There are so many processing steps that are done to actually create, again, the device that we eventually put in different electronic circuits that we have. All right. Then after this, the devices are made onto the wafer. Typically, they will go through testing and then packaging and then essentially shipped either to manufacturers or to the consumer to buy. So again, most of the fabrication that happens for this occurs in the nanometer scale. Right? Now, what I want to do here is to let you appreciate how far we've come when it comes to electronic devices and obviously humanity here. So I'm going to play a video, hopefully, please. This is called Moore's Law. All right.
Number of transistors and extremely small conducting lines for electric current. Now we can use
Oh, because it was on mute. All right, so all right, so it was about something we call Moore's law. And Moore's law is actually a prediction and not necessarily like a law of physics. And it was predicted by one of the founders of Intel called Gordon Moore. And what he predicted was that the number of transistors that we can fit on a chip would double every 2 years. And that meant that the scaling of the transistors would decrease over time. But as time has gone on, we've run into issues with obviously making these transistors small, right? Because you can only make them so small. So research actually has allowed us to now think about more interesting ways to make these transistors without just scaling them and making them smaller and smaller. So typically, or the transistors that we had in the past, up until somewhere around, I would say 22 nanometers, we had it as a 2D type of transistor. And then to, again, be able to increase the performance, they changed the structure to make it more 3D transistor. And different companies have different structures that they work with, again, to increase the performance of the transistors so they can, again, fit more transistors on a chip and have us have these devices that are pretty powerful. Right? The past, the naming of the technology was based on something called the length of the channel. That was used to describe the technology that was being used. So these numbers that we see on the plots here, on the y-axis where you have Elvin, and then on the x-axis where it's supposed to be the dates, they named the different technologies based on the smallest channel length for the device. But now you'd hear some companies say, let's say, for example, the 7 nanometer device or 7 nanometer technology, and they are no longer really talking about the channel length anymore. And the reason why is because, again, the structures of these devices have changed. So they kept the nomenclature really for marketing purposes. And so they will keep decreasing the numbers, but it really doesn't represent the channel length anymore. Again, this is mostly for the inorganic electronics. All right, so the next video that I will show here, this is the current technology that we have. And it's pretty incredible when you watch this and what, again, we've been able to achieve when it comes to creating these devices. Now, the video is going to talk about a specific system. The lithography system, again, is the way of transferring patterns that we want onto a substrate or the silicon wafer. So the image that you have on the right-hand side shows light. This is light that is passed through something called a mask or reticle. The mask has patterns that we want to actually transfer onto the wafer that we have. The wafer that we have. Okay. Yeah. Okay. Okay. Yeah, no, I'll just keep using my mouse. The wafer that we have down here, right? And from the reticle or the mask to the wafer, lenses are used to focus the pattern onto a small area on that wafer. Right. Now, the specific system that we are going to look at costs somewhere between $200 and $300 million. Obviously, it's extremely expensive. So you can't have too many companies, obviously, that are going to be able to make these devices. Resolution of the devices, again, which is the smallest transistor that you can essentially make, is less than 13.5 nanometers. All right. And for this specific system, you need about 40 shipping containers, 20 trucks, 3 Boeing 747, yeah, I know, to be able to get it to the fabrication lab. So I'm going to play this video. Let me unmute friendly. And with this video, actually, when you see it, first of all, the light that is being used to generate the pattern onto the wafer is one that is actually created. So it's not found naturally, but they create that light, which is marvelous. Actually, it wasn't. Otherwise, I have to link that again. I can open it. I can open it here too. Do we need to do anything else if I open it?
The video. It's embedded.
Yes, it is, but it's something. So that's why I created a. I wish I came up with that idea. Okay. So now with our appreciation of the inorganic material devices, if we think about people like me doing research at the university, there's no way we can afford this. So that will bring us to organic electronics, right? So organic electronics is, again, falls within the area of material science. And typically when you hear organic, you're thinking about food, but that's not what it is. It's actually coming from the fact that the materials that are used in these electronics are carbon-based, right? We know that for humans, majority of our matter is made up of carbon. And with organic electronics, these carbon-based materials tend to be synthesized. So most of them are not found naturally, which kind of goes opposite to what you think organic means, but usually they are synthesized. There are two categories of materials that fall within organic electronics. They are either small molecules or polymers. Small molecules are, again, materials that are synthesized. Polymers, typically just examples of polymers, plastics fall under polymers. You have some ceramics that fall under polymers. Silk falls under polymers. Some fabric falls under polymers as well. The good thing about organic electronics is that we can actually tune the electrical and chemical properties. So again, it makes changing its properties pretty, I wouldn't say easy, but at least possible through research. And it also tends to have great mechanical properties as well. So typically, people that study within this area usually are looking at design of maybe device structure, synthesis of new materials that can be used in the organic electronics, fabrication and characterization. So after the materials are made, and if we want to make it into devices, what kinds of methods can we use to make it into devices? So we tend to stay away from lithography, which obviously is very expensive. And characterization is, again, figuring out the properties or the performance of these devices, and then the applications that we would have with organic electronics. So I'll first kind of start with some applications and then kind of go deeper into the fabrication. Right. So one advantage of organic electronics is that they tend to be low cost, right? Much more cheaper than the inorganic counterparts. And the reason why is mainly because of how they can be processed. They can be made through solution deposition methods, which we will see. They really don't require high temperature processing methods. Typically, if there are methods that require high temperatures, those tend to also be expensive. And some examples will be inkjet printing. So if you think about, again, the printers that we have, they can actually be used to make electronics. Stamping is also another method that can be used. There's something called roll-to-roll processing, which is transferring a pattern from one roll to another roll of the substrate, and again, creating the device onto the substrate. The other advantage of organic electronics is that the substrates that are used can be flexible, right? So we can use plastic as a substrate. So when I say substrate, what I mean by that is for the inorganic one, we use silicon, which is mostly rigid. With the organic ones, you can pretty much work with silicon, but we can use different types of substrate. We can use plastic, we can use paper, we can use fabric as substrate. And the good thing about it is that we can make these devices flexible. So I'll give you an example. We've all seen the Samsung foldable phones. All right. So the reason why those phones are able to work is because the devices or the electronics that are made on plastic display. Right. So they can still work on the plastic display. Now, the reason why the entire phone is not flexible is because batteries haven't caught up to the electronics. So with batteries, they tend to still be rigid, so they still need housing for these, whereas the display itself does not require a rigid surface for it to work properly. Right. So again, that's an advantage of having the organic electronics. The images that I show on the right-hand side, where the top left is the display. Again, you can think, we don't quite have this yet, but think of having a tablet that you can, again, just roll out the display from the tube, work on it, and then roll it back in, right? Without having to be concerned about it breaking if it falls on the floor. We've all seen the curved types of OLED TVs. Again, they are made with electronic, organic, from organic materials. Right. An advantage of, or another application where organic electronics can be found will be with sensors, right? So we have made electronics that can actually mimic human skin, and they can sense pressure, all right? They can sense maybe with athletes when they are running, if they want to take some vitals, you have these electronics that can also sense them as well. Something we don't quite have yet, but a technology will be to have something called a pay-as-you-go organic solar cell. Again, making it cheaper so we don't have to depend on the distribution. How about that? Well, you all know. All right, so these are some of the applications of the organic electronics. Now, what I'm going to do is now focus on a specific material, because there are so many materials that fall within organic electronics, but pentacene is a very common one. And I'm not going to go too deep into the chemistry of it, but the rings that we see on the right side, they are called benzene rings, all right, and they are just fused together. And that's what makes the pentacene. There are 5 of them. All right, so 5 benzene rings. The good thing about this material is that it has good charge transport. And by charge transport, what I mean is that it allows for pretty good current to flow through it. Right? The disadvantage of the pentacene is that it's not soluble in organic solvents. And one advantage that I talked about with organic electronics is that we want to be able to fabricate them or deposit them through solution. So researchers kind of thought of a way to change it from being insoluble to soluble. Because it's not soluble, typically the position of this material would require high temperatures, that again, something we want to avoid. And the conductivity, or again, current that flows through this material is not optimized. So to optimize it, There are these side groups that, again, chemists came up with to change the material itself and make it from being insoluble to soluble. And now that it's soluble, what we can do is now think about different ways that we can deposit this material so we can get the best current out of it. Right. So the advantages of making it soluble or adding the side groups is that it increases the charge transport. It makes it environmentally stable. However, the film morphology, which is essentially when it's deposited, what the film looks like is not typically the best if you just allow it to deposit on its own or to form on its own. Right? And not having good film morphology can affect the conductivity of the material. Right. So what we are going to look at next is just different methods that have been created to deposit the specific tip sensitive material. Before I get into the deposition, I want you to at least know why getting a good film morphology is important. The two images that we have are called transistors. There are two types of transistor structures. On the left side, it says bottom gate, top contact. The gate and contact are just electrodes or metal contacts that we can actually connect probes with to be able to measure the current out of the device. So there are three main ones. The source on the left side, the drain on the right side, and then for the bottom image or image A, the gate is at the bottom. Right? And then for the right-hand side transistor, we have the source and drain again on top, and the gate is at the bottom. But if you notice, there's a difference between the image on the left and what we have on the right. The one on the left says the contacts are top contacts. The one on the right says the contacts are bottom contacts. You notice that the semiconductor for the left is below the source and drain. And for the right-hand side, the semiconductor is on top of the source and drain. Right? So that's the difference maybe between those two structures. Now, the organic electronic material, the material that we actually work with, or what we are going to try and manipulate is the semiconductor material. Right? So the TIPS pentacene is a semiconductor material. And ideally, what we want is for the semiconductor material to bridge the source and drain contacts with no obstructions. So we don't want any gaps in between. We don't want any, I'll say, grain boundaries, which is, we want a pure crystal that goes from the source to the drain without having like lines in between. Or essentially, if there's a gap right across, then you're not able to actually have conduction happen. The reason why, we can think of, let's say, if you have water that is going to flow through a pipe, right? If at some point the pipe is broken, right, then once the water gets to the pipe where the pipe is broken, it's going to flow out. So you wouldn't have conductivity or you wouldn't have the water flowing. It's the same with the semiconductor material. We want it to be able to bridge the source and drain contact with no obstruction between the source and the drain. Right? So ideally, we want to ensure that the crystals look like the image that we have on the right-hand side. I would say the best one would be to just have one big crystal, but that is not attainable. So typically, the individual lines that you see on the right-hand side will be individual crystals that would bridge your source and drain contacts. So we don't want the image on the left. We want our crystals to look like the image that we have on the right-hand side. So we want to avoid crystal disorientation. Low aerial coverage, again, these are crystals on the substrate. It means that you can't have the best performance out of what you have here. Crystal aggregations are when the crystals kind of develop on top of each other. We don't want that either. We don't want too much variation in the thickness, again, of the deposited crystals. And essentially, we want to ensure that our device performance is good. Right? So the different deposition techniques that I use typically want to achieve these. So the rudimentary technique is known as drop casting, and I'll say is the worst of all of them. And what drop casting is essentially taking the semiconductor material, which is a tip sensitive. It comes in a powdery form. And then it's dissolved in a solvent. One common solvent is known as toluene. And once you dissolve it in it, you get a solution that is then deposited onto a substrate. So that's what we have on the left-hand side. Then what happens is that for drop casting, you just allow the solvent to evaporate. When it evaporates, it crystallizes over time. But with drop casting, because you are not really directing the crystallization, again, it crystallizes whichever way you want to, right? So some methods that have been, I'd say, generated to kind of get over the challenges that you have with drop casting. One is dip coating, where you have the substrate is dipped into the tip sensing solution and then is drawn out of the solution gradually. And as it's drawn out, again, right at the top, your solvent evaporates. So as it's drawing out, it starts to crystallize. So you will end up with pretty-oriented crystals. The disadvantage of this method is that it wastes material because you end up having crystals forming on both sides of the substrate, and you only need it on one side, right? Then we have solution sharing, where the substrate is heated, the solution is put on the substrate, and then the sharing plate is essentially dragged across the solution, and that again orients the crystals. Again, this doesn't give you the best crystals because there's rapid crystallization that happens, and when crystallization happens rapidly, you tend to have gaps in between the crystals. Then we have zone casting. Zone casting is also one that has tried to orient these crystals. The disadvantage here is that the crystals are oriented in a perpendicular manner, and we typically want it more in a horizontal manner. And then the last type will be the off-centered spin coating. And what it does is it uses surface tension and centrifugal force to essentially drive the solution on the substrate outward as the substrate is spun on a plate. Right? And then crystals form on there. Again, the crystals here tend to be very thin and they are not very stable. So with these in mind, what I wanted to do was to come up with a method that would overcome these challenges, and that is what the temperature gradient technique is, right? So the idea of the temperature gradient technique is to use a force to control essentially the crystallization and control the direction of it, and also the size of the crystals that we get. The second method, which is the blend approach, approaches that people have used, and I ended up developing that on top of the temperature gradient method, and we'll see why. Right. So again, the technique here is to control, again, how the crystals form. All right. So what is the temperature gradient method? I'd like to walk around. I feel like I'm all right, so what you have is really what you can't see here is a metal plate, a metal plate on the left-hand side and a metal plate on the right-hand side. One of it is heated and the other one is not, right? And what happens is the heated plate obviously would be the hotter side of the temperature gradient, and the metal plate that is the support and the room temperature will be the cooler side of the temperature gradient. And we put this this is just a petri dish that is put on the metal plate. And what happens is that your gradient again goes from warm to cooler, and that is what is going to drive the crystallization. And I'll explain how it drives the crystallization in a bit. Right? The crystal growth direction actually starts from the cool end and grows towards the hotter end of it. Right? So this image actually shows a bit more of the temperature gradient method. So the substrate that I use here is a silicon substrate. Again, the material is tryptopentazine that I want to crystallize. And with the temperature gradient, I'll give maybe a simple example of everyday, I'll say food that we know. So when you have, let's say if we take 2 tablespoons of water, all right? And we take, let's say, 1 teaspoon of sugar, and we dissolve it in the water. If it's at room temperature, it will dissolve, right? If we add another teaspoon of sugar, it will get to a point where the sugar will not dissolve anymore, right? However, if we heat it up, it will dissolve, right? So that's the idea behind the temperature gradient method. What we need on the cooler side is called nucleation side. So we need a bit of those solutes in the solution to create a seed layer for crystallization to happen. And then on the hotter end of it, all the solutes would have dissolved over there. So crystallization starts happening on the cooler side because again, you have nucleation side on the cooler side. And as obviously the solvent evaporates, you have crystals forming from one end to the other. And that's how the orientation is gotten. In terms of the crystal side, I'll focus more on the image on the right-hand side, where we have the nucleation that we have occurring, typically we call it supersaturation. So you have the solute, when it's really saturated in the solvent, we call it supersaturation. Now, if you have low temperature gradients, your supersaturation tends to be low. As you increase the temperature gradients, the supersaturation tends to be high. So in region 1, you would get a good crystal size even with the low temperature gradient. As the temperature gradient increases, your crystal size will still be good, but there's a point where you pretty much diminish, right? The crystal size starts to decrease. And the reason why is because there's a competition between nucleation and growth rate. You essentially want growth rate to be higher than the nucleation rate, because if you just keep nucleating, you just have these solid particles in the solution and they are not going to crystallize, right? So we usually want to remain in this region for good crystal sizes. So if we just look at a single crystal that is created, on the low temperature end, the nucleation dominates. So crystal sizes tend to be smaller. Somewhere in the mid-temperature region, the growth rate tends to be higher than the nucleation rate. So the crystal sizes start to get larger. And then kind of towards the higher temperature end, the opposite occurs again, where nucleation rate now starts to supersede growth rate. And the reason why is because on the high temperature end, evaporation is higher, right? Because you have high temperature there. So the solvent evaporates a lot more. So nucleation tends to happen faster over there. So the crystal size starts to decrease again. All right. So in using the temperature gradient method, there's pretty much 5 different temperature gradients that I tested. The image A is just drop casting. So these are optical microscope images. Just drop casting, again, you notice that these crystals are really again, they crystallize in the directions that you want. You have too many gaps. You have these like deposits of the testament thing which we don't want. But then immediately using the temperature gradient method, you start to see good crystal alignment. However, the area coverage is not good. These yellow parts that you see are the substrates, essentially. So you don't have good coverage, but the more we increase the temperature gradient, the crystals start to bridge each other and the gaps reduce. And obviously, by the time we get to the 6 degrees Celsius per centimeter, you have great crystal sizes. You don't have any gaps, but if we compare that to this, which is the 3.5 degrees Celsius per centimeter, the crystal size is small because again, we are using higher temperature gradients there. So what we, after obviously attaining the crystal, the type of crystals that we want, what I did was then to actually characterize it. So what kind of area coverage would I get? What kind of orientations am I getting from the substrates? For the area coverage, it was just doing line scan over the substrate and essentially comparing the area that was covered with crystals to the entire substrate. And for the crystal orientation, again, line scans, but pretty much counting the number of misorientations that we have from the crystals, right? So the image on the left is just showing the area coverage for the different temperature gradients. On the x-axis, again, our temperature gradient increases. On the y-axis is the area coverage. As the temperature gradient increases, our area coverage essentially increases. It gets to the point where this looks a little flat, and the increase is not as steep. And the reason why is at some point the crystals would already have bridged each other. So then your increase is only incremental. With the crystal alignment, however, again, with the increase in temperature gradients, crystal, so on the y-axis is misalignment. So the lower the number, the better it is. All right, so our best performance is around 5 degrees Celsius per centimeter, because once we get to the 6 degrees Celsius per centimeter, we end up with a misalignment again, a more increase in misalignments, which we don't want. Right. This just shows an image of the surface roughness of the crystals. The blue line, dashed line, is without temperature gradient. You notice how rough that surface is, because with every value that you have, is essentially the substrate surface, and every peak is a crystal. And then the red line is one with the temperature gradient method using the 5 degrees Celsius per centimeter. Again, showing an improvement in it. All right, so after doing the crystal morphology characterization, the last thing I did there was now test the conductivity, because again, the whole goal of this is to make sure that we have a pretty good conductive device. So the image that we have, the top image, is actually an optical image again of the brown portion of it is the semiconductor material, and the yellow are your contacts. And they're actually made from gold material because you need it to be metallic to be able to conduct. So we probe that device to get something that we call mobility. And mobility, again, is just the conductivity. All right, so the mobility for this is 0.035, which wasn't as high as I wanted it to be. So I had to, again, investigate why this was not as high. But it was still better than the mobility without using the temperature gradient method. All right, so what I realized, the reason why the mobility wasn't as high as I expected was because there were cracks in the crystal that I didn't realize when I used the method. And the reason why is because there was stress in the film. So obviously there are cracks in the metal, then you're not bridging the source and drain contacts the way we would want it. So then I had to again try to figure out what will prevent these cracks, and that's where the blend method came in. So adding a polymer to the solution, because then that would again allow flexibility. So when the film develops, you don't get cracks in it. And I tested 4 different polymers. The best one was the top one, which is the P alpha MS, poly alpha methyl styrene polymer. All these chemicals have like long names, so we just abbreviate them. Again, use the same temperature gradient method. The biggest difference was that I mixed the tip synthesis, which was the semiconductor, with the polymer. Now the polymer is not conducting. So then you think, well, if you're going to mix a semiconductor with a non-conductive material, would the mobility not go lower? We'll see why they actually improve their mobility. So again, using the same temperature gradient method, the images that we see here are polarized optical images. Image A is just it's a simple drop cast, again, not using the temperature gradient method. And then B through D were with different amounts of polymer added to the semiconductor. So B was 1:1, so 1 part semiconductor, 1 part polymer. C, 2 parts semiconductor, 1 part polymer, and then D was 3 parts semiconductor, 1 part polymer. And as you notice from the optical images, again, the crystal sizes were good, coverage was good, so there was no huge difference in terms of just looking at the morphology. The average mobility, however, showed a drastic difference in the devices. The 1:0 ratio is just pure fantasy. The 1:1, it will be 1 part fantasy, 1 part P alpha MS. The 2:1 showed the highest average mobility. And then the 3:1 dropped again. So then I was wondering why, again, from the morphology, they all look the same, but why do we have such a high jump in the conductivity? And what I did was some type of characterization where I actually looked at the cross-section of the film. So what happens actually when you blend the materials and they crystallize is that they separate. It's called vertical segregation or vertical phase separation. So this is a silicon substrate. And then the tip pentacene, although it was blended with the polymer, actually separates from the polymer. So the polymer stays on top of the tip pentacene, which makes the film, again, look good and not have the thermal cracks. But then the semiconducting material doesn't mix as much with the polymer. And when we come back here, with a 2:1 ratio, you have a concentration of 29% of semiconductor in that interface. So that allows for, again, pure conductivity. Right? So the best was a 2:1. And then the last thing I did was to test it on a flexible substrate. So throughout, I had used a rigid silicon. And what I did was to now actually create it on a plastic substrate. And that actually gave me the best performance. So that brought our mobility to 0.5, so at least more than 10 times higher than just doing the pure systems. Okay. And that is pretty much the work. Okay. So, are there any questions?
Shall we do it again for? You would agree that that's an excellent presentation, excellent work being done by Kyeiwaa, a Ghanaian lady. What I didn't say earlier was that she actually went to St. Mary's.
Yes. Yeah.
So she went to St. Mary's in Accra, and then is at the forefront of doing this remarkable work. And for those who are a bit confused, I know our civil engineer friends are like, what are civil But we have seen the field of electrical engineering that does not get too exposed, that we do not see so often. And of course, as she spoke about the flexible stuff that we are using, this is the kind of work that underlines why maybe your phone will be more flexible or all these variables that you have. And you have a lady actually doing all this work. Shall we? And I think when, as she was talking about what she did with the temperature gradient technique, which is something that she's done herself, my mind went to what we used to hear, like allotase constant and all the things that was being said at the time. Right? This is something that has been done in her work. And so, shall we come with it? And I think I would say for us, you know, when you do electrical, you think that it's only physics and maths.
Yeah.
But you see chemistry in there. So for young people who say that I'm going to do electrical, so I really don't need chemistry. And I should leave it behind. Tell them that there is use for it. And of course, there was stress analysis, and all that, you know, come into play. So everything you are studying is important. Never think, you know, I saw some videos where everybody said that all those things that we learned in school, we don't know what they were for, but we see how important they are. So thank you very much, Kyeiwaa. We will take a few questions. I don't know if anyone has a question or has a contribution that he wants to make. And those on Zoom as well, if you have a question you want to ask, a contribution you want to make, you can raise your hand. Yes. So, Mommy, Kyeiwaa's mother wants to ask her a question. She's a banker, but I'm sure she's going to ask some engineering questions.
I'm sorry I'll disappoint you, but now, I guess appreciating that you know all that she's been doing. And the thing that comes immediately to my mind is, why would you want to, you know, get yourself into such complicated things? And what kept your mind to want to do a thing like this?
Okay, well, thank you for that question. So I would say this is an area that I did not know very much about until I went for my doctorate. As I was looking at the different researches that the different faculties were doing, this is one that I read up on and I found interesting. So that's kind of how I ended up working in this, and obviously stayed in this because still find it interesting.
Engineer past president Andrew Toto come forward and answer this question.
Well done.
Thank you.
Material science, that into the sky there and other things. It's not easy to appreciate it. But when you use your computer and the semiconductor, then you really understand. But this your method, we saw the advance in the inorganic one.
Yeah.
Well,
Yeah.
invested.
Yeah. Yes. Yeah.
How are these your temperature gradient technique being applied now?
Okay, so that's a very good question. So part of the reason why we're doing the research is to make these electronics cheaper for us. As we realized with the inorganic ones, the processing tends to be expensive, and then obviously eventually trickles down to us, the consumers. And we see our devices, obviously, again, the performance are much better, but they're not cheap. So the reason why we are doing research in this area is to come up with new processing methods to make these devices cheaper. We haven't gotten, obviously, to the point of the inorganic ones because they've been doing this for ages. And I would say one huge boundary to getting the industry to switch to the organic ones is they've spent a lot of money on the infrastructure that is currently in place, and they keep trying to improve them. So we would have to come up with something, obviously, that supersedes what they have for them to want to obviously invest in it. Yeah. So we are not there, but there's a lot of work that is being done, and there are a lot of advantages also on the side.
My question is almost similar to what past president has asked. And I guess I was going to use the word scalability.
Yes.
Moving from
the
micro level or not the public or nano level to the other level where the processing, obviously the infrastructure will be built.
Yeah.
But then I would suspect that there should be a parallel let me call it research into how to build equipment or the infrastructure for the methods that you have developed. Thank you. You see, after all the civil guys.
I also agree to generic electrical questions. Yeah, there is some work that is being done to scale them. That is not the area that I'm in. But I do know research has been done where they actually created devices that are not just those individual devices, but a couple of them. They, again, not at the point of the inorganic ones, but still a lot of work being done there. And with also equipment that we built for this as well.
Thank you very much. I don't know if you get any questions from those online.
No, that's
At the point, we had about 60 people joining online. And I want to see if there's any questions. Let me check the chat.
I don't see any questions yet.
So we also have a form for attendance on the chat page. So if you're a member of the institution, you can fill the form to indicate your attendance. I know Kyeiwaa also expressed the interest in encouraging more girls into science because she mentioned that that's one of her passions. So I would just like her to say a few words on that to encourage some. We have some students also that we invited to join us. So we'd just like to hear a few words that you have for them.
All right. Yeah, I'm actually, I'd say it's one of the areas that I work towards ensuring that, one, with the females that I end up lecturing, that they don't see themselves as not as competent, right? So I typically would encourage them a lot, but these are obviously ones that are already at the university level and have decided they want to do electrical engineering. But the ones that haven't yet, I'll give an example of what I've currently our job recently in Ghana. So I'll tell you about the past week and last week, I guess. Yeah, I visited quite a number of secondary schools, and One was to get them to apply to universities, and I actually visited more of the female schools. I'm trying to visit one of the male ones. But part of the reason why I wanted to be there was to show them that I was once like them, right? I was a science student sitting in the seats that they are currently sitting in, finding difficulty with some of the subjects, but at the end of the day, as I'll say, from that point of view where it seems some of these are unattainable, it just really comes down to dedication and hard work. That is purely what it is. And I say that they can also achieve, if they want to get their doctorates, they can also do it, but it takes a lot of commitment and a lot of hard work. So that is what I have done again since I've been here. And I continue to encourage the people ones that I come.
Thank you very much for the great work. And I believe you met engineer Professor Elsie Kaufman. I spoke with her and then she mentioned that she had met you. So I believe there's a lot you can do with her. She has some stuff that she's doing in that direction, that space. And of course, I believe what you're saying is very inspirational, especially for our lead engineers, because we also find that most of them tend to branch off and live into other areas. I mean, I know some who, just as I said, they don't want to have anything to do with engineering again. Then they went off into insurance and finance, but the pinnacles that you got into shows that if they just have to continue pushing themselves, everything is possible. Everything is open to them. So,
I want to add one more.
Yes.
And one more thing that I'll add is not for them to be discouraged when they find themselves in positions where they are probably the only females there, because that's currently what my position is. In my department, I'm essentially the only female lecturer, and it's always interesting watching, I'll say the men. I'll stop there.
All right, we understand. So we'll take the final question from the guy Dr. Kyeiwaa, the chair of the Engineering Council. So, brief of, I don't know. Dr. Wachi, please, you can go ahead.
Professor Kyeiwaa, good job. Yeah.
Thank you.
Lecture. Yeah. Yeah. I had, this technology keeps changing. And I keep thinking that now we've got inorganic, we've got organic. Is it possible to have a hybrid?
There actually, I would say, is a bit of a hybrid, because even with what the presentation that I just went through, with the material that I was actually using, there's this organic material, but it was based on an inorganic substrate, which is silicon. So there are applications where there is a hybrid between the two. Yeah.
I see. Yeah.
Take a final question. What is the next?
I have a full-on question.
Doctor, please.
And what is, does Moore's law still apply when you have the inorganic the organic electronics?
So the structure of the organic electronics, they are mostly based on the, I'm going to focus more on the transistors, because the transistors are the basic devices that we're using. They are based on the inorganic structures. So it essentially is following the same trend as the inorganic ones.
I see. Okay. Thank you.
All right.
Thank you very much, Dr. Boachi. Yeah, past President Dr. Boachi. We have the last question. What is the next step in this research, and where do you see this going?
All right, that's a great question. So there have been different directions. One, what I'm currently actually have my research students doing is applying the temperature gradient method to different semiconductor materials. Because yes, we've seen that it works very well with TIP synthesis, but what about other semiconductor materials? So I do have some of my research students working on that. I also have some research students working on coming up with a different method. I actually taught a class this past spring, which was new. But what I did was I made my students kind of work in my research area. And the good thing was that they came up with their deposition methods that, again, proof of concept. So we're able to actually deposit these, I made them use tip synthesis again because it's well known. And they use different deposition methods. And it was great to see just the outcome or the results of some of them. I suggested to one group to use electric field. It was actually one that I started using when I started doing my PhD, and I ended up abandoning that to do the temperature gradient. So I suggested one group, actually for them to do it, and they were able to get the alignments. Not the sizes that I have for the temperature gradient, but they were able to get good alignment. So that would be something that I would want more research students to work on. Some other method was using capillary force, again, to align the crystals as well. I'm also kind of obviously doing the deposition methods, looking at different materials is one area, but also just looking at different applications as well. One of my research students, I had her work on making wood into transistors, which is, again, when you think of wood, wood is not conductive, yes. But then, again, with that, we've been able to get some good results. Waiting for her to write a paper on it. But we've been able to get some good results on that. So I'm also looking at different areas that kind of veer a bit away from what I am currently doing. I've done some work also with in optoelectronics that instead of using electric field for conduction, it actually uses light to conduct electricity.
Amazing. All right. Shall we give her a final applause for all the great stuff that we've heard? And I believe as a parent, sometimes they're like, what is our daughter talking about? You know. Dr. Mati, you still have a question or a contribution or your hand? Yes, you have.
Maybe it was from
Okay, maybe. I think it was the previous. Yeah. So we want to also give her another hand of applause. Thank you so much, Kyeiwaa. And it's been good having you and having you in person and being here with us. So we thank you so much for the time. We thank all those who have also been able to join us this evening. Whether you understood something or not, I believe that you have something to carry away. Her smile alone is inspiring, so you can take that away. And for all those who joined online, at the point that I said we had about 60 people joining us. We hope that next time when there's a program here, you will come in person. It's good to see your faces and to put the faces and the names together. So we want to join us here. But we are grateful for this evening and the time that we've had. So once again, thank you so much.
Thank you.
I heard Prof. Kyeiwaa, you are a professor. No,
I'm working my way there.
I'm sure
I'm assistant. Next year I'll be associate, and then hopefully in a few years I'll be full professor.
Definitely. We can't wait for that. We'll be there to celebrate with you. Thank you so much for the time. Thank you. Thank you so much. So, ladies and gentlemen, this is the end of this evening's seminar, and thank you for coming. We pray that as we all go back, the Lord will take us safely back to our destinations. Amen. Thank you. We have some few refreshments at the back, some water, nothing so special, but you can grab something and then you can carry along. Thank you very much.
And then your mommy has such.
Now your questions are all answered. Your questions are all answered.
I don't even know what my daughter.
I know, I never was that stressed.